pipes. Hello, hello. Okay, I'm going to shut that off. Stay in put. Go ahead and say hello.
Hello, hello. Yeah. Oh.
That's good. I think it's best to put this like in your back pocket, bend this over your shoulder, or hook it on your belt if you have a belt.
Yeah, no belt.
Or throw
I
it in
can
that
put
pocket,
it.
whatever
Yeah,
you're comfortable with.
that's great.
That's great. And then if you want to shut it off, just tap it to shut it. I think actually no, hold it for one. Like 1, 2, 3.
One, two, three.
Yeah.
Awesome.
Okay, let's see. Are you live here?
Now I
Let's
need
see.
to.
You need to see, or are you going? What's your
You
help with the questioning yet? Hello, hello. Do you have any friends?
Everybody can hear me? Yeah, awesome. Cool. Yeah, I think we'll make it timely, so I'll just go ahead and start. In the spirit of efficiency of this conference, this actually might take less time than 1 hour, so hopefully I'll be able to give you back some time for the rest of your day. Nice to meet you, everyone. My name is Noam Levy. I'm the field CTO in GroundCover. GroundCover is an observability company. We do eBPF-based tracing and metrication of applications. Today, I'm going to discuss hopefully the fourth pillar of observability, which some of you may had experience with in the past, called profiling, and how it is becoming quite powerful and even more accessible than ever, and it's a really good time to engage with profiling more and more. So profiling is a very powerful concept. It is becoming very accessible, much more accessible than it used to be, and we're going to tap into how it became accessible. And most importantly, soon enough, if things are going the pace that they are going, it's also going to become much more frictionless. So let's talk about why profiling is powerful before we discuss its accessibility. So a small 101 on profiling. Anybody here had experience with working with profiles in the past, application profiling? Yeah, it's one of those pillars that is, I would say, the most intimidating of them all. Very hard. It's a bit hard to consume. We're going to tap into that as well. But in general, profiling gives us a lens into how resource allocation is done by our application and by the third party the application is using. Not just CPU, but also memory. In this session, I'm going to mainly discuss CPU profiling, which is I would say the more popular pillar, although memory profiling is also a very powerful technique. When we talk about profiling, there is a concept of ad hoc profiling. So for those of you who developed in Golang, for example, and use pprof, then we can ad hoc create profiles on a running application. And there is the concept of continuous profiling, basically doing profiling on running applications, even in production, for a long period of time, and see how our application is behaving throughout the life cycle. And it gives us fairly good granularity, so we can get basically up to the function call level when we're looking at our application from the lens of profiling. Why we profile applications? So when we discuss why we do things, a better way to think about it will be what kind of questions we try to answer when we profile application. So example questions is the most basic level when we talk about CPU profiling is where our application spends most of its CPU in which procedures. For another pillar, another type of question, and this is also going back more to memory profiling, is where do my application is doing allocations and deallocations of memory throughout the life cycle. This is where stuff like garbage collection activation kicks in when we profile applications. And finally, and this is kind of like the issue that everybody is looking for, and very rarely it is the issue, is that we try to blame the garbage collector for why our application is slow. TLDR, usually it's not the GC fault, it's how you use the software runtime that you are working with. But that's very, like people sometimes look into a profile and they see like this big chunk of like GC free. Yeah?
Can we check file system related operations?
Yeah, so this is a great question. Profiles also gives us access to SCaLE operations, and we can see how much time, and depending on the profile configuration, we can also see how much time our application is idling, waiting for SCaLEs to fulfill. So also network operations, file system operations, and yes. Few words and terminologies, just to set the level straight, that you might hear those terminologies. I think that especially when we're talking about profiling, I can tell you that even me getting ready for this presentation, it's really, there are no dumb questions, and sometimes things are being communicated as simple, while it's not necessarily simple, and it's actually very crucial to understand the basic terminologies in order to have a good understanding of what we do with profiling. So when we investigate profiles, usually this is the picture or the kind of visualization you're going to see when we're looking into profiles. We call these flame graphs. There's a lot of work around how you visualize and how you color flame graphs. It's a whole philosophy, and I'm going to tap into that once we're going to look into some examples. The way we profile applications and we time operations is by walking the stack or unwinding the stack as calls are being done. So in the profile picture that you can see here, for example, as we go up is more and more nested function calls within the original, let's say, wrapper call. And basically, profiling is the act of walking through that stack up and down and time the procedures and how much time they took. And another terminology, another word that's going to be centered to this presentation, it's not related to profiling specifically, it's just a big enabler to the accessibility revolution and the frictionless revolution that profiling is having, is eBPF. Anybody here heard about eBPF or used? Awesome, wow, that's like so, the amount of hands being raised when we speak about eBPF in these conferences gets higher every year, and this is a great news. So we're going to tap into that, and great. So now let's talk about accessibility. What is accessibility? And sorry that it looks like I'm dumbing down the conversation, but I think it's very important to understand what questions we're trying to answer together here. So accessibility, at least the way I look at it, is how easy it is for me to implement a pillar or a signal into my application. And the other side of this coin is how easy it is for me to consume this pillar. How easy it is for me to get conclusion and actionable items, because generating signals in applications, yes, sometimes it can be hard, but why go through this if I'm generating signals that end up in a dashboard that nobody is making sense, or more importantly, taking actions according to those signals that I was generating. So let's talk about implementation of profiling. Profiling is kind of a fragmented field. It's runtime sensitive. So every software runtime has its own, especially binaries and software runtimes that are not compiled just in time, like Rust binaries or CPP binaries. They have their own issues when it comes to profiling. It's a pillar that people here usually, I assume that a lot of people here have experience with traces and with metrics and with logs. Those are pillars that usually appearing in a single or a unified on a very few observability systems within an organization, while profiling was kind of like the advanced pillar that only a very small portion of the engineers in a company had the ability to even work with and to implement. So it was never really contextualized with the rest of the pillars and with the rest of the signals that application was generating, which is bad. We want contextualization. We want to look at a metric in the light of the profile that we had. We want to look at a profile in the light of a trace that we got. Also, there were big challenges when it comes to operating system compatibility with profiling in the past. There was a tremendous work in operating systems, in Linux specifically, in making it more profiling friendly. By the way, and I'm going to mention it in the end, there is a person that I highly suggest looking into his blog, and he's probably one of the most amazing engineers of our time, especially around performance engineering, named Brendan Gregg. He's one of the main contributors to eBPF and also into the concept and making profiling an accessible technique for engineers. And he's speaking a lot about the compatibility journey with profiling in his blog. Highly recommended read. So these are solutions that are implementing profiling today, used to at least. So Elasticsearch, Parka is a popular profiling project, and Grafana's Pyroscope, which is a backend for profiling, and we're going to touch it as well. These days, and hopefully some of you also heard about it, anybody here heard about OpenTelemetry? Awesome. OpenTelemetry is a pretty revolutionary project that basically has the mission of aligning the way we generate and ship telemetry from our applications, regardless of the vendor. One of the, I would say, the core issues of observability, historically speaking, is that the concept of observability were evolving in proprietary landscapes, in proprietary vendors, and it made the action of adoption and moving from one solution to another very hard. OpenTelemetry kind of like basically won in the last 3 years, I would say, got super mature, and it is now pretty much the universal and the go-to framework when you want to make your application generate signals and to ship them to the vendor of your choice that you are using. At this point, most vendors, if not all of them, are OpenTelemetry compatible. And those who are not are in serious troubles going forward. So far, OpenTelemetry standardized the way we generate and ship logs, distributed traces, and metrics. But profiling as a signal was never standardized. A year ago, I believe it was a year ago, maybe it's almost 2 years ago now, the signal of profiling as a separate signal was standardized by the OpenTelemetry project. It is still in beta. I would say that the ecosystem around profiling in OpenTelemetry is still very much experimental. It's something important to have in mind. But there is the acknowledgement that profiling is a signal that needs to be standardized, and it has an experimental support in OpenTelemetry Collector. And I created also a lab for you to try out, and I'm going to share it in the end of this conversation. Why it's important that we'll have a standardized ecosystem for generating signals. First of all, it allows us to be portable. In an era when there is ever-ending innovation, our ability to adapt technologies into our code is something that is very important from decision-making that will make sure that our decision have a long-term outlook, a long-term runaway. We don't want to adopt proprietary technologies to our applications, especially around instrumentation, for example, without thinking about, well, is this going to be a trouble soon if I want to, for example, try out another solution? Another point, and for me it's not less important than the actual maturity of the project in any given point in time, is how referable the project is. The moment we have, as software engineers, a reference that all other software engineers are using, it's much easier to adopt technologies. It's much harder to adopt SDK just relying on the docs of the vendor and not relying on examples from open source solution that tens and the dozens and hundreds of other organizations are adopting themselves. This is a very powerful primitive to have the entire industry across different companies with different challenges aligning to the same terminologies. Basically, we're all of a sudden speaking the same language, while in the past we're all speaking different languages. And another very important thing about OpenTelemetry, that across the software runtimes, across the different configurations, the semantics are aligned. There is no different semantics or environment variable or configuration when we talk about OpenTelemetry in CPP compared to C#, compared to Java. That concept in OpenTelemetry is called semantic convention, and it's very crucial for the universality of the project itself. So let's do a small OTTL 101. OpenTelemetry also referred as OTTL. Let's do a small 101 of how OTTL pipeline looks like. So when we talk about telemetry generation, especially about the pipeline part of it, not the consumption part of it, which is not universal still, there are 3 steps. We receive data, we modify it, and we export it. And that's the same terminology that we will use in the OpenTelemetry configuration. So this is an example of a simple OpenTelemetry configuration. OpenTelemetry configuration will define a receiver. Other than the spec and the collector binary itself, OpenTelemetry also define a protocol, which is called OTLP, OpenTelemetry Line Protocol, which is very important because as long as we ship data also from OpenTelemetry SDKs or from OpenTelemetry solutions, they are all consolidating to the same endpoint. They are not speaking in different protocols, less ports, less configuration, all aligned to the same endpoint. Then we define a processor. A processor is where we define mutations on the data that is being received. For example, and my talk is going to focus on Kubernetes environment, doing profiling in Kubernetes environment. In Kubernetes, we have the concept of enrichment. So we get data signals, but we want to enrich them with the metadata of the pod namespace service name. So processor and OpenTelemetry is where we are able to do this kind of enrichment. In processor step, we can also do drop and filtration and static upsert of values of our choice. And lastly, we're going to do an exporter, which is where to ship the data after the reception of it and the processing of it. What's cool about OpenTelemetry, you can ship the data to multiple exporters. And then, last step, you can see here that I'm defining the service, where basically I'm creating the chain of receivers, processor, and exporter. And this is very cool because I can create multiple pipelines that every pipeline can, for example, decide to take only a set of receivers, run through a set of processors, and ship to select exporters. And each service pipeline can really ship to different, I can drop the data in a bucket for long-term storage, but only a subset of it, and then I can ship it to my observability vendor with a different retention period, and so forth. So it's very declarative, kind of like the same philosophy that we have today behind Kubernetes, and very, very flexible. This was the part of the collection of the data. But what about the generation of data? So usually when we talk about OpenTelemetry and observability about signals in general, we used to have to do something called instrumentation. Instrumentation is the act of mutating our code, inserting code into our applications to generate signals from within. The pros are obvious. What are the pros? Is that we are able to control where and what is the scope of the signal that we're generating. The engineers know their application the best, hopefully, right? Theoretically speaking. Problem is that the same pro is also the biggest disadvantage of this method, is that we rely on engineers to generate the data. So in a sense, when we observe applications, we want to have an angle of, I would say, zero trust to the signals that we generate. If we are bounded by what engineers are doing in their applications, then potentially we have blind spots in our application. Think about it like security-related aspects. If an organization would say that they are secured because engineers are not clicking on suspicious links because they swear they don't click on suspicious links in their mail, that's probably very bad security. Good security is having malware detection, antivirus, phishing protection elements that are not assuming that they should trust the users or the actors. Same kind of posture will be super beneficial for observability as well. So how do we achieve it? I'm going to discuss that soon, but this is where basically the challenges and the state of implementation ends. Now let's talk about consumption. We were talking about accessibility. These were the challenges of implementation and how OpenTelemetry unblocks them. Now we need to discuss consumption. So as I mentioned, observability, profiling is a pillar that is hard to consume. Like I can give you an example. Most people always look at a flame graph. Half of them at the beginning think that the x-axis is time, which is never is. And then everybody was like, okay, so what's where things are going? What does it mean? Or they see that the most time is spent on the GC, on the garbage collector, and they will be like, okay, then what do I do? Like it's not my code, right? I just allocated an array. Like how can it be so slow? Why the garbage collector takes so much time? So it's hard to understand, and so far only few humans in an organization could make decision based on it. But we are now in the era of agents, and we have a superpower that can take the same profiling data and help us, even if not remediate it completely at this point, but can help us see through the complexity of profiles. Now, Will I tell you that that agent street profile is perfect? Of course, the answer is not. This is not LinkedIn. I'm not going to tell you the end is near because I was able to figure out a profile. But it's definitely something that can help you go through the hurdles and to give you context about profiling as you look at the data. So generally speaking, going forward, the assistant of AI or the ability going forward of AI to potentially even get conclusion from profiles leads to the bar of using profiles and make benefits out of it much lower. So if we solved implementation, or like not solved implementation, but at the very least implementing profiling now is an effort that seems to be a long-term beneficial effort. There is no vendor locking when we're talking about implementing profiling anymore. And the consumption of profiles is only going to get easier. Then maybe it's a very good time in software engineering to introduce more profiles and to push organizations to use this pillar that can provide huge benefits when it comes to performance engineering. The last remaining question, so how we actually put this all together and make it a frictionless experience going forward. So let's speak about eBPF, for a second. For those of you who are not familiar with eBPF, eBPF is a kernel sandbox that basically allows us to load programs that gives us visibility into running applications and to running operations within the kernel. The program is loaded agnostically to the user programs that we're getting data from. The notion is that we basically hook operations in the kernel and in the user space, and then we're able, using specific functions, to exfiltrate data from those running procedures. As Brendan Gregg, one of the ushers of the eBPF revolution, put it once, this is like putting JavaScript in the kernel. This is basically the times that we live in. Here's a small example of an eBPF hook. So the way it works, we basically load a program that is decorated with the point where we want to hook. In this case, you can see that I'm loading something called a kprobe that will hook a syscall called doUnlinkAt. Unlink is the syscall that fulfills the deletions of files on the disk. And basically what is going to happen here is that I'm loading one program that every time unlink syscall is being invoked, this program is going to run, and the program under it is called a kret probe hook, basically hooking the return from the syscall. So when we're back from the kernel to the user space after the unlink syscall was fulfilled, this second program is going to run. Within the probe, I have a limited set of instructions that I can run, and as a result also, and this is the sandbox aspect of eBPF, I have a limited set of finely tuned and very well thought of functions, which are called eBPF helpers, that I can use within the probe. In this case, what you can see in the example here is that whenever I do an unlink, whenever an unlink syscall is being invoked, I'm going to print using a special print helper that eBPF, the sandbox, provide us to show which process, it can be the RM command, for example, is invoking the syscall, and for which file name. And as the syscall is being fulfilled, and the syscall is done, and I'm going back to user space, my unlink kret probe is going to run, and then I'm going to print the results of it. This is, by the way, a fairly old example of the kprobe is I'm not sure if it's the old school way, but now we also have new primitives in eBPF for hooking kernel events. We use fentry and fexit now, which are a bit more performant, although kprobe does allow an extra flexibility. There are tons of other there are a few other probes that we can use with eBPF. eBPF can also use to shape network traffic. This is the famous, for those of you who are interested in network performance using eBPF, Meta are probably the leading organization of implementing eBPF at planetary scale. Every packet in Meta goes in goes through an eBPF program these days. And we have open source projects like Istio and Cilium that are leveraging eBPF to do network shaping. And we are also able to do probes on user-level applications as well. What does it mean that we can do it in terms of like, even I would put it as like a business objective? What are we unblocking using this technique? So eBPF unblocks the technique called zero instrumentation. Basically, we can now generate signals about applications without requiring engineers to modify the applications themselves. This is a huge primitive for any organization. I can now generate signals about applications that are being developed by tens of thousands of agents running from engineers that are looking very, very briefly at the output of their cloud code or of their codex or cursor or whatever generated code. And without relying on whether the code used instrumentations, I can still generate signals about potentially and surface new behaviors that these applications are presenting. If having zero instrument, I will tell you that when we even started ground cover 5 years ago, we're still big believers that observability cannot rely on instrumentation as a whole. It cannot be like a strategy for organization to assume that all the signals will be generated by engineers. This was 5 years ago. Today, with AI, with agentic development, this is the amount of software that is introduced into production, which much less oversight, is unprecedented. We're basically shipping 100 times more code in some environments with much less attention to the code being shipped. So the ability to generate signals without relying on instrumentation, just as a concept, without even talking about profiling, is pretty much essential to us guaranteeing reliability of the software that we ship. So at eBPF, we were able to do signal generation for metrics and for traces. So we can do APM, we can generate spans, we can generate metrics about latencies, about HTTP endpoint calls, about the SQL transactions. And now, finally, we can also do it for profiles, for profiling. So remember all the vendors I named earlier, Elastic and Grafana and Parka. Basically, we are all, and the biggest ground cover is not doing profiling, so I can't take the credit for that. But the other vendors that were invested in profiling in the past are kind of all consolidating into the OpenTelemetry project as well. Actually, I would say that Elastic did the extra mile of even contributing a patented code that they do for creating profiles for stripped binaries, which is pretty cool. And basically, having this in OpenTelemetry, like having in OpenTelemetry an eBPF-based pillar that generate the fourth signal of observability in a universal way that is going to be compliant with the spec that every other observability vendor and every other pillar in your organization is aligning to, is basically like amazing news for everybody who's interested in observability. So, and the last benefit of it, obviously, is that we do not need even instrumentation to get started with it. So how do we start? So we discussed the OpenTelemetry collector and the backend. This example is going to be based on Kubernetes, but we're going to set up a pipeline together which contains an eBPF agent. It's going to ship to an OpenTelemetry collector, like we introduced, and it's going to ship the data to a profiling backend. We're going to do this all in Kubernetes, which is just very easy to deploy applications to once you get through the hurdles of Kubernetes themselves, but after that it's pretty straightforward, and if you're already running application in Kubernetes, you're going to just get immediate value out of this. So let's start with dissecting the pipeline one by one. Start with the agent, right? We need to emit the signal, so we need to deploy the OpenTelemetry eBPF collector. Few things to know about eBPF agents in general. eBPF agents are privileged. When you hear about a technology that is based on eBPF, most probably, like 99% of the time, just because I'm hesitant to say 100% of the time, you will need to run it as a privileged container with access to the host system. Access to the host system in Kubernetes means that we need to give it access to the process namespace. We need to give it explicitly the security context privilege true, or add the capabilities like sysadmin. And we need to mount the host volume. In Kubernetes, we need to mount the node, the volumes itself into the pod file system. So the container has access to the entire proc namespace and the entire sys subsystem within the running host. Next, we have the collector. Not sure if the text here is too small, so I'll just go through what it says there. We're going to have an OTLP receiver because, as we mentioned, OpenTelemetry eBPF Profiler is an OpenTelemetry project. Hence, it complies with the OTLP protocol, which is fantastic. We're running this in Kubernetes. When we do stuff from eBPF, we have no idea of the notion of pod, of a namespace, of a service name. We need to somehow enrich it into the incoming data. OpenTelemetry has a really cool processor called K8s attributes, Kubernetes attributes. Basically, you tell it what is the association encore within the incoming data, and then it will request from Kubernetes the rest of the metadata. The profiler, the eBPF profiler in OpenTelemetry, knows the container ID. The container ID is good enough association encore for the processor to complete the rest of the information. And lastly, we need a backend. So backend is still the proprietary part. This is your vendor that supports shipping profiling data. In this case, I took what was the simplest open source way to get started with a profiling backend, which is Pyroscope. Now, the backend for profile is going to be a database. When we speak about the databases in Kubernetes, we would usually want to attach them to a disk and make sure that the controller that deploys the controller that deployed the application is aware that this is indeed a database. So in Kubernetes, this is called a stateful set controller, and this is the controller we use to deploy database and data-sensitive applications. We have all this in place, and how this is going to look like. So this is basically what you're going to look at once you're going to port forward the backend or access the backend itself. You're going to get immediate catalog of all your applications in the Kubernetes environment. And for each application you're going to press, you're going to see a flame graph. Now, the flame graph, depending on the backend, as I told you, coloring is a big philosophy, a matter of conversation in flame graphs. Pyroscope out of the box will show you based on the package. So each color here represents a different package. You can also just do the hue based on the nesting or based on the length of the CPU time being spent. And there are other techniques. So for example, Brendan Gregg, his flame graph generator allows you to generate a flame graph that is going, like for example, for Java applications, going to show you when this is like Java code, when this is JIT, and when this is like the CPP JVM underline code. So you can decide, depending on like what makes sense to you when you're looking into the application, you can decide on the hue itself. And again, I get this information about how much time is being spent in the application without doing any changes. So you can take any development cluster that you have running applications in, your application is going to appear immediately in the Pyroscope UI, and you're going to be able to look into the profiles. This is a good, now we were talking about how promising this entire thing is, but it's important to say, this is still an experimental signal and an experimental eBPF agent, still early days, not necessarily in the sense of stability, but in the sense that there are a lot of changes being, that are breaking changes happen in this pipeline. However, it is still all happening within the unified ecosystem of OpenTelemetry. The other challenge is symbolization. So I didn't explain symbolization quite thoroughly when we began. When we do profiles, we want to have meaningful names in the flame graph, like what is the name of the function. Sometimes binaries, when they shipped into production, are going through the act of stripping. Basically, we take the symbols out in order to keep the binary small in production and fast. In CPP, for example, we are stripping away the dwarf data. The dwarf is where we have the debug symbols in binaries these days. The current philosophy, if I understand the spec correctly, and the plan is to allow the backends to allow you to load symbols. So you ship the profiles with offsets, and then there is going to be like a resolver that is going to resolve those offsets to the actual symbols. It is important to say this is strictly a problem for stripped binaries, and specifically Golang, for example, which is probably popular here. Even though it's a compiled binary, Golang does not have this issue. Like with Golang in OpenTelemetry BPF collector, specifically they are like special case in Go because you can always extract the symbols. And then Node.js, Python, all of those, again, no issue. Interpreted languages, no issue. Let's look into some examples now. So, ground cover, for example, I'll tell you one of the challenges that we constantly face. We run an observability backend at the customer premise. We don't run it in our cloud. Basically, our UI component in the cloud is a very simplified, I would say, if to put it simply, it's a fancy proxy. We get the request and we we delegate the request to the customer backend, and then we serialize the request, and then we ship the data back to the browser or to the client that is requesting the data. Not a lot of things that can go wrong, right? But for us, for example, what we discovered when we turned profiling for the first time, not now, but earlier, when we looked into some of the scaling issues, when we got a lot of like requests going on in the solution, we saw that we spent like a lot of time compressing data. So all of a sudden, we understood that we can like potentially gain like really cool wins just by looking into better compression algorithms or better compression libraries that are focusing on zero copy or introducing some novel techniques, or potentially even to be on the lookout for bugs. We had like a very nasty, it was we saw it through a memory profile, but like 2 years ago we had like a very nasty gzip library bug, and that by moving to a fork that introduced a fix to the allocation process, we were like cutting down the UI service memory by like 40%, like something crazy. We saved a lot of money with AWS that day. But this kind of operations, like for example, looking at your application and all of a sudden just realizing, wow, like compression, I never like gave it too much thought. You know, you use the standard library, like I never thought that maybe moving to deflate from gzip or trying snappy can do magic to my AWS billing or to my application performance in general. And all of a sudden, the peripherals of your applications are getting like this light that was very important for us. The other thing is blocking operations. So it's not appearing quite well, but as one of you mentioned here, so for example, when we delegate work to the customer backend, we are basically in a non-blocking, we don't have a reason to block. We're waiting for a response from the server. With profiling, you can also opt in for looking into the time spent idle. So it's a very excellent pillar and a very excellent tool to understand if your application is idling and to let you, to shine light on areas where like, oh, maybe I can introduce some concurrency in this procedure and stress the CPU and make like more meaningful work. For example, for us, one of the areas where this is very interesting to look in is middlewares. So the concept of middlewares, for those of you who don't know, HTTP middlewares, is that I have my endpoint that the engineers are implementing an endpoint that returns, for example, amount of logs. Between the endpoint that is returning the amount of logs and the request coming into the HTTP server, there are a bunch of middlewares that are crucial before I let data out, right? I have security middlewares. I have role-based access control middlewares. So I need to make sure that the user requesting the data has access to this data. I'm checking a database. So all of a sudden, before I'm even hitting the logic of the application, of the endpoint itself, I might have a query to the DB that is taken out of time. So yeah, obviously we cache, but when cache is being invalidated, how much time I'm spending on the query itself. It's also important. And when you do tracing, like general tracing, sometimes you can miss those kind of operations, or you see that the middleware took a lot of time, but you don't necessarily going to see within the span, depending on your instrumentation. Again, depending if the engineer put it in the instrumentation, you might not get visibility into what made that middleware, specific middleware, running for so much time. So that kind of visibility that is not relying on the quality of our instrumentation and that shines light on areas that intuitively we're not thinking about when we're doing performance tuning is crucial for us delivering the best performance possible. Another very cool thing for ground cover and for people who use your eBPF is that all of a sudden we're able to see the overhead of our own eBPF U probes. So I told you that we have, so we remember really need to zoom in into those examples. Sorry about it. I will explain what's going on. So we have here, what you see here in the above the light blue part of the flame graph, where it started with ASM, there is this big purple chunk. This purple chunk is a read of, is an SQL read operation. This is we use the JAX-C PGX driver for Postgre queries in Golang. When we do the read operations, like the way our solution works, every time we see, not in just our applications, but in customer applications, a DB read operation, our eBPF sensor U probe, because this is still happening in the user mode. So I showed you K probes, which are kernel probes. This is a U probe that we load to the SCaLE library call. We ask for some times from the CPU to take away the payload, basically the SQL query that was being shipped to the SQL driver. This is how we provide visibility into how much time SQL query took and give visibility into the SQL query itself. For our customers, it's very important, and for us as a company, we cannot do these kind of things without giving the utter assurance that we're not going to steal a lot of CPU time. Now, eBPF basically kind of like already makes it hard for vendors to hurt the application performance themselves. But all of a sudden, I have this tool that allows me to check the performance and the latency that I inflict on SQL calls myself, which is very powerful. For, let's say that assuming that you're going to use eBPF tooling on your applications, so up until now we discussed the peripherals such as like the gzip library that you're using. Your applications are probably also behind the scene being blocked or not being blocked by U probes and K probes and eBPF code that is being loaded. Now, most of the time it's going to be fine. You're going to see these days a lot of eBPF K probes and U probes in your profiles because for most of the CNIs in Kubernetes, in networking, for example, these days leverage eBPF. But it is again another example of how much we don't know about how our application actually behaving in production at scale. We can do much more. So we talked about the third-party effects. We didn't dive into kernel here. So you can also see in profiles how much time you spent in the syscall before application time and not just in the user mode. And there is also the concept of memory profiling. So the OpenTelemetry eBPF profiler is limited for now for CPU profiling. You can also, for example, in Go, you have the pprof library which allows you to do memory profiling as well. And then you can see how much allocations are being done and how much memory is being allocated by specific functions in your application. That's another great visibility pillar that I suggest trying out, probably the easiest way to start, at least that I'm familiar with memory profiling, is with Go, because it's a tooling within the Golang ecosystem. It's literally one import that you add. Yes, unfortunately, it relies on instrumentation. And then you get this fancy web UI, and it's very easy to generate profiles from your applications as well. Starting to conclude here, profiling data, especially with the example that we just seen, really complements what we call the 3 traditional pillars of observability. We call them MLT, metrics, logs, and traces. There's a huge debate, I'm not going into it, whether there are 3 pillars, there are no pillars. It's a hot topic on LinkedIn. I'm going to stick with the legacy definition, at least for the data type perspective. So we used to work, most of us, in terms of people who instrument code with metrics, logs, and traces. Profiling is definitely a pillar, a new signal that complements and empowers this data. It really allows us to start do observability flows, such as the 2 that I wrote in the slides here. So for example, I can start with, everybody looks at latencies of their applications, and then they look into spans. Now, knowing that I have profiling data, continuous data, and I see that I have the span of this specific middleware takes time, now I can start adapting the mindset of, okay, let's see the profile data and see why this middleware takes so much time. And I can also start from the other way around. So I can start with my suspicion from the profile file and add instrumentation or look at the traces and have a much better metrication or instrumentation in place. So for example, I can decide that maybe it's not a good idea to generate a span that covers the entire endpoint fulfillment, but maybe I will generate a span just for the querying part and a span for the compressing part, so I have it in a more convenient way in my system. But for me at least, and at least from what I see from an observability vendor perspective, at least some of us, really try to push for the dream of a single pane of glass. I believe that the observability is not about getting data from a specific data point that your application is generating. It's really crucial, especially in environments like Kubernetes, to understand how a specific data point plays along other data points that happens during the same time. It's never an investigation of a single data point that gives you all the answers. It's the ability to understand what happened, what was the node, CPU, and memory, while my application took 5 seconds to process a request, or whether the node was in an unready state. Why there was a huge memory spike while my application was sending 500 error codes. It's always a matter of context, and our ability to streamline profiling into the same data lake, the same pool of the other pillars that we have, and not make it a tool for the advanced user for the power users in the company, is probably a huge factor in reducing mean time to resolve and to have better understanding of how applications are behaving. Now let's speak about AI. So I had to do this try because this is this is the call of the hour. And I opened ChatGPT Atlas, and I opened it on Pyroscope. I just told him it's very hard these days to stick to the English grammar of it when it comes to agents, but I told it to tell me what's wrong with this profile. So it actually did kind of a good job. Now, it's my fault that I gave him a very specific profile in time where I think I just started the eBPF profiler, so the most of the time was spent on hooking the running applications, at least from what I understood, and I actually didn't know. But this, the first call that it's written there, the aggregation _pre_ handler, is related to K-pop loading. And so I think that I was like very enthusiastic. I just launched the profile, and then I was seeing a lot of time being spent on the eBPF hooking procedure. But as I went down, it kind of nailed what I kind of knew about this application. It pretty much nailed down that I need to look into the gzip implementation and the JSON encoding implementation, and suggested to look into operations that are putting more emphasis on zero copy and more performance, and making sure that I'm not double encoding or gzipping, ungzipping before I'm shipping the request itself, which is pretty amazing even at this point. So together, and then I was thinking, okay, eBPF kind of like unblocks generating signals without human intervention. And then AI from the other end and agents are able to analyze the signals without human intervention or with very minimal orchestration or guidance. This like plays along really well. And this allows me from, I wouldn't say anymore like a software engineer perspective, but like from an operator perspective, to take this method and to leverage it while I'm writing software. One of the things that we are like, that at least now I'm trying when I'm writing code, is to connect with MCP to my solution, to my observability vendor, which is my case myself. And when I'm letting the agent generate the code, I'm asking for it to rely on the data coming from production. Now, this concept, regardless of profiling, if we zoom out for a second, if you think about what is missing for agents more than anything else when they are generating code today, it's not the code. We do 1 million context window these days. Context is no longer the issue of the code. The only thing missing in the context is how this application actually behaves in production, how this application actually plays out, what alerts the engineer and the business have on this application. And all of a sudden, without even relying on the agents to generate instrumentation data, I can make the agent potentially write much better code, much more senior code, by leveraging data points about how applications actually behave, which I think is, we talk a lot about harness and how to optimize code generation these days in agents. This is, in my opinion, at least the next 10x for agent efficiency when it comes to the quality of the code being generated. What I want you to remember potentially from this session. So profiling adoption becomes easy or more straightforward or more something that you can rely on for the long term, because we're now using standardized tools. It's only going to get better from here. Like, this is a very good time to introduce something and then get happier every 2 weeks, because the releases are kind of like huge. It's not like it's less about regressions, more about, oh wow, they introduced this, oh wow, we still had oh wow, it now takes twice less memory, wow. It's like, we still have a lot of wow moments, so it's nice. Our applications are doing a lot of stuff that we are not aware of. And eBPF, together with agents, but eBPF as a deterministic technology that is already mature and available, really unblocks a human-agnostic observability. Not in the sense that humans are not needed, but in the sense that we are not relying on the engineers to generate signals that are crucial to understand the applications. And as I mentioned during the talk, I also want you to take away to go to the Brandon Gregg blog from here and dive into the wonderful world of profiling as well. This QR code will take you to a profiling lab that I created for you. The idea was simple because, by the way, these stuff are not simple, unfortunately, today, so it took some time. But the idea is to hopefully, if you have a running Kubernetes environment with application, to run a single command of kubectl apply, and you're getting the entire lab up and running without any configuration. It's going to deploy it in its own namespace. It's going to load the daemon set. It's going to do the Kubernetes metadata enrichment for you, hopefully. And let me know in the issues. I made it a public repo. If it's not working out of the box in Kubernetes, let me know. I'll try to make it very convenient for you. Yeah, any questions? Yeah.
Thanks a lot for the talk. For those of us who don't have Kubernetes, for example, I have a SCaLE application, and on my laptop I want to build my own eBPF program, right? And I want to start and to collect data. What steps should I do?
So if you will go to the OpenTelemetry eBPF collector library, the GitHub repository, you have you have the ability to run the agent locally on your machine, and it should work as well. Once it will generate the data, I would still recommend shipping to, so I don't have this lab working, I will just give you the outline. You probably want to run Docker that will run the pyroscope and the OpenTelemetry collector as containers, and then just run the eBPF collector locally on your machine where the Go application is running. At that point, you're going to get your profiles. You're just not going to get the nice name. You are getting from the eBPF collector, the tags that you will have is the PID and the process name. So you are going to be able to find your application still. Just not going to be like fancy. But yeah. Yes?
Yeah, while you were talking, I was trying whether eBPF I can run eBPF on my Mac. It doesn't seem to like it. I mean, I haven't run a Linux VM on it. Is that the case?
So running eBPF is not like just compiling the program. There is a tooling around wrapping and loading the applications. There are other repositories that I suggest using when you're trying to package a binary that loads eBPF program. I believe that Isovalent, yeah, if you will go to ebpf.org, there is like an foundation around eBPF. Isovalent, I believe it's either, I think it's, Cilium provides like a packaging for eBPF programs. And I don't know to answer like what potential issues you have there. Oh, it's a Mac, yeah. You need to run a Linux virtual machine on a Mac and then like run it there. Yeah, it's mostly for Linux, this technology. There is like an eBPF for Windows. I don't believe it answers to the same spec. I'm less familiar with this project. And yeah, it's not supported for Mac as well. Yes, behind you there was another question. Yeah.
You said that you think it's a good thing if we have developer-agnostic signals. Why do you think that is a good thing?
I don't think, okay, so I think it's a good thing because I want engineers to still be very involved with the code, and I do not believe that eBPF is going to solve, it's not going to make them unneeded or like make the familiarity with the code unneeded. I believe in eBPF as generated data as a compass for engineers. I want eBPF, I want to have a layer, for observability at least. I believe that I want the ability for engineers to think from scratch about their data points, but I also want to produce some hints regardless of how confident they are feeling with, how their application actually is running. For example, we are not doing OpenTelemetry in ground cover, and like I really believe in instrumentation as a culture. I just think that instrumentation as a culture is much more efficient if it is being built on a bedrock of signals that are decoupled from the instrumentation effort itself, if it makes sense.
That seems like it would be a failure of planning to not leave adequate time for developers to understand what they are building.
No, I don't think it's about making them not understand what they're planning. I think that I can be only certain to a specific level about how I'm familiar with the project, especially when we're not talking about low-level projects where engineers have incredible intimacy with the code. And to be frank, like in terms of at least what I see in reality, software is not, especially in the agent era, software, practically speaking, is not being developed by people that are looking for being intimate with their code as much as possible. It's just simply not the way modern software engineering, unfortunately, works. I wish people to be like more like Linus Torvalds, for example, who is famous about not adopting CPP into the kernel because he wanted to understand just by looking at the code how what is going to happen behind the scenes. This is potentially the pinnacle of how software engineers need to be familiar with the code. Unfortunately, potentially, I would say 80% of the code written today is generated by people who are just very amazed that Cloud Code got the code one-shotted. They wrote a post to LinkedIn about it, and all of a sudden people are being reliant on the code that a lot of software engineers gave very little thought of. So I want eBPF to hint them and give them like this nudge that, hey, there are potentially some stuff that you want to dive deeper into. This is at least my take on it. I'll be happy to take this conversation after if you wish. Yes?
Normally, when I'm running a program on a single processor, I use the GPROC to find out which function takes maximum time. Then I distribute that into some processors to make it. It looks like eBPF here is a good tool for that.
eBPF basically lets you, depending on how many eBPF program you load, and to get almost ability to hook software in a lot of meaningful places across both user application calls and also kernel application calls, regardless of how many applications are running. The notion of like if I would say usefulness is a question of what you're looking for. Like it's depending, like what would you like eBPF to tell you about?
I wanted to tell that which function takes most amount of time so that I can make that function.
Yeah, you can definitely with eBPF generate signals like we saw it with the profiling example, like tell you where CPU is being spent the most time in the application as well itself. Yeah. Any other questions from that side of the crowd? Okay, awesome. Thank you very much. We're just at time. Really appreciate everybody taking the time to attend, and have a great rest of your day.
1. That's good? All right.
Hello, my name is Shannon, and today we have Amir Jacoby from Sawmills AI, who will be presenting making OTTL go brr 40 times. Go ahead. Let's give a round of applause to Amir.
All right. So, Amir. I work for Sawmills. Before Sawmills, I was VP engineering at New Relic. I managed the incident management group and learned a lot about observability over there. And I'm going to talk to you about a story that we have that started in Sawmills back like startup. We started about 2 years ago, year and a half ago. And one of our first customer, we migrated them from, no, it doesn't matter. And we had an issue. Like they started telling us that their observability are missing logs. They have data, they have crashes. They have no crashes, no spikes. They're just like nothing, but they're missing logs. We're going to talk about the incident. We're going to talk about how we investigated that. A deeper dive into OTTL and how it works, how we fixed that. We did a bunch of very, very cool, my opinion, optimizations to OTTL that are still not released, still not part of OTTL, but maybe. Benchmarks and what we learned along the way. Thank you for joining me on this journey. So what is Sawmill doing? We're doing something very similar to what we just discussed. We're coming in between the agents, not AI agents, though I know it's like very in right now, but you know, good old agents that collect logs, metric, maybe traces, and we connect to them, and from them we integrate to them and send the data back to Datadog, New Relic, OpenSearch, like any vendor you can think of, whether it's open source or closed source. We analyze the data at your premise and send it back to its destination, and you can make decision and reduce your cost by using the product, and it's quite significant. So we rely very heavily on the collector. So OpenTelemetry, for those who doesn't know, is an open source that started as an SDK and an API of like definition of something called OTLP, which is the OpenTelemetry protocol. And it's defined how, it started with traces, define how traces, logs, and metrics should look like. And there are a lot of SDK all around that can export those metrics, those telemetry data in general, out in a very nice and standard way. It's actually the second most active CNCF project after Kubernetes, so if you're here, you probably know it. So the collector itself is the Swiss Army knife of OpenTelemetry. If you want to collect logs, you can use it just from a machine. If you want to analyze and drop logs, you can use it. And we're going to talk a lot about OTTL. OTTL is sort of like the language that allows you to do a lot of the stuff that makes the collector awesome. So we're going to talk about that a lot. The collector is comprised of 3 main parts. There's also other things, but basically receivers, which allow you to process receive and collect the data either from other sources or from a file or wherever you want. And then processors, you can filter, transform, batch, do things like memory limit and anything else you want. It's very easy to extend. And then you send it out. So, you know, input, you do something, output, very standard. And processors are very interesting because they gotta process every log record, every telemetry data. So, you know, a lot of processors mean a lot of processing. So our constraint as a company, we're basically, our main operation is we're running first at the customer premise, right? So we're running, let's say, in your Kubernetes cluster. And that means, and we're there to help you manage your cost. We're there to help our customers figure out what's going on in their telemetry data and help them reduce it. So we're not there to increase their compute or memory or any other thing. So that constraint made it very, very critical early on in our journey as a company. It makes it very important to us to really understand how the collector operates behind the scene. So what happened? What was our incident? So we installed our collector at a customer. Everything looked good. You know, we at least in our eyes, we processed about 40 terabyte a day for a cluster that wasn't necessarily a single collector. It was a few, but one cluster, 40 terabytes a day. We migrated most of their transformation from that vendor, and those were over 300 very complex regexes and grok and you know, regular transformations. And quite honestly, I don't think the people that designed the collector really thought about that, like so many transformation and filters in the collector. So it was pretty intense. We even needed to figure out how to load all the configuration file because it was so large that you couldn't put it in a config map. So we had to like write something that would load it from S3. Anyway, every log record needs to get through all of these OTTL expression, and it looks fine for us. Like, we're cool, it's working. We even did some performance tests before, and it all looks good, right? But it wasn't really good. We're starting getting, you know, calls about like, look, there are logs missing. We can't see everything. We're not understanding where it's going, and we're telling them, no, the collector is fine. It's something else. And it took us a while to understand that like something is really, really wrong with the collector, and we don't have any visibility into why. We gonna go over the next slide, but basically, there's a lot of metrics the collector is great at that, but the metrics you get from the collector are from the collector. So if you start processing a lot of data in the middle, and let's say you have four processors, and you know you have 8 Go routines that are receiving data in a loop and trying to process them, and all 8 of them are in the middle of processing data, and there's a lot of traffic coming in at the same time, you're going to find yourself hanging. The processor will start, the process, I mean, would start hanging, and you wouldn't really be able to process the data, and the collector wouldn't know because it basically it doesn't know that it has incoming traffic that's supposed to come to it, right? Let's see what else I'm missing here. Yeah, so basically rejected connection before the receiver could even see them. That's the bottom line here. So what did we do to actually get visibility? So sidecar is a really nice pattern that I personally really like. It allows you to take, you know, in a pod, and you have your main container, and you can attach as many containers as you want. So what we've done, we actually already had another container that sent telemetry data about the collector because we don't want to contaminate the working of the collector. So it's kind of funny. We're a company that is doing telemetry, like observability for observability in a sense, and then we had another level which is doing observability on the observability of the observability, you know. So yeah, and what we added on top of that is an HA proxy sidecar that would sit in front of the collector and would analyze all the incoming connections to that collector and would let us know whether incoming connections are actually accepted or not. So that actually, you know, opened our eyes because suddenly we were shocked to see that the collector is actually rejecting most of the connections. And we had no idea that that's happened. There's like zero visibility into the incoming connection into the collector. So that was amazing. Another thing that I really like about the HR proxy is that you can actually configure quite simply fallbacks. So the first thing we did is say, okay, if the collector is not able to process any data, just send it to the vendor. So we started moving to a methodology of like identity functions, of like saying always receive the data and send it in the same format, so you can basically do a fallback or a circuit breaker if you want. And that was really awesome. So we had the rejected connection, we had a lot of latency. I think the 80 percentile was about 10 seconds, which, you know, is crazy. Really, we had a few really bad days back in the time. See pretty much what I just said. So when we started looking into what the collector is doing, we assume, and we were right that there were too many OTTL expression basically, which again, you know, title of this call, of this session. So we had too many OTTL expression. We weren't able to accept connection because there were no Go routines available to accept the request. gRPC rejected at the socket, like before, there was no really available receiver. The collector had no idea. We had no visibility. So the HR proxy allowed us to first gain visibility into what's going on. Then we started going deeper. So, you know, we basically took a lot of the logs from that customer and started doing some load testing and profiling the collector, and quite fast we saw that the OTTL eval was the culprit. And more specifically, when you look here, you'll see that the allocation and value comparison and resolving path were part of the, you know, were the one that took the most time, basically. So allocations and OTTL, let's talk about that. So we'll do a deeper dive into how OTTL works, but basically every OTTL evaluation means going through an AST, an abstract syntax tree. And the abstract syntax tree is generic, which makes sense, right? So it gets types of any, and then it needs to box them. It needs to like takes a string and box it, and boxing means allocation. Allocation is not good for us. Resolving path, like traversing the AST, is also quite, it's actually very efficient. Like I tried different AST engines that are not OTTL, and OTTL was really, really efficient. So I don't want to like say that it's not. It's really built really well. But still, you need to traverse a tree, and if you can avoid that, that's better. Lookups over generics also not that efficient because it means boxing again. Any boxing, when you go over 300 filters, which is what we had, and you have allocation, you get to like 600 to 1200 allocation per log record. And you know, when you have a lot of record per second, it's just too much. And I didn't even start talking about what it means for the garbage collector that needs to do something with all those short-lived objects. So we had a cycle where we had more location, more garbage collection, which slowed down the throughput in a way that's very hard to see. We got more back pressure, more retries. There's AST, abstract syntax tree overhead, which really impacted CPU. Over some you know, open source that's very hard to, you know, OTTL is a very deep part of the OpenTelemetry collector. So we didn't really know what to do at the beginning. Like the first thing we did, like start checking whether some of the, you know, just, okay, so let's remove some of the filters. So we tried doing that. We removed some of the filters. We removed some of the, try and simplify some of the regexes. But eventually we ended up with about 200 filters, and we still had the same problem. So we dug a little bit deeper into OTTL. So what is OTTL? I think I already gave you, you know, a hint, but OTTL is the DSL that's built into the collector. It allows us to do things like filter, transform, and route. It's declarative. It's very nice. You can attach it to the YAML config file or any like YAML representation. It allows you to not dynamically, but without compiling the without any compilation, to attach and manipulate those log traces and metrics and go into all of their fields dynamically. Had a lot of interesting built-in functions. You can check if things are, you know, their types. Basically, it's a language, and you don't need any custom code, but you need to do interpretation, and that was the main issue that we had. Right? It's still when you load OTTL, it goes through a phase of evaluation, so it doesn't stay as OTTL. It's been translated, like I said before, into an AST, but still not very, still not optimized as it can be. So this is how a log record looks like when you translate that into a JSON. So you got the body, you got some, you know, fields there, you got the attribute, the level, the status code. You know, I think pretty standards. And here's an example of like filters. So you have checks that you gotta check if, like you wanna manipulate the body first, you gotta check if it's a map, right? And then if you wanna check something inside, you can do things like contains and go into attributes. If you don't do the check at first, you're gonna get an error. The error can be ignored or not, but it's always nice to check. And you can complicate it. You know, add and between, you can do nested fields, you can call regexes or grok, very, very nice. All of this is translated into a tree. I'll show you an example pretty soon. And you gotta evaluate a lot of it. Like we had about 3 million evaluations a second. So when you start and look into the profiling, we saw that simple kind of comparison, or basically had 1 allocations and took 57 nanoseconds. Sounds like, seemed very, very fast, but it's not. It can be much faster. 3 allocations here, and very complicated, had like 4 allocation, and you know, like a lot, it takes a lot of time. So the reason is partially the AST and quite frankly things we didn't get to, which is the regex. The regex is also terrible. The Go regex is so it's really not efficient. There's going to be a call out about it pretty soon. How we translate OTTL into an actual thing we worked on, the collector works on. So there's an expression, it's being parsed, translated into a tree. And then every time a new log message arrives, you gotta walk and traverse the tree. So you're gonna visit, you're gonna go and turn the expression, attributes level equal error, and then you gotta go and check the, and traverse it. So you start with the end, and then you do the comparison, you know, and then I'm sure you're here and you understand what I'm talking about, but basically it's a lot of operation, all this traversing, even though it's quite efficient. Those expressions are static, and the data changes, but because they're static, you know, quite honestly, we can just compile them. That was my first, when we got into this project, my first impression was, oh, cool. So AST, it kind of reminded me of my classes about, you know, languages, and that's very nice. You can take an AST and basically turn it into code, right? So what goes nice, it actually has this library called Gen. So let's just translate it into code, and that's what we've done. We actually wrote a parser that takes AST and translated it into code using a library called Gen. That took us a few weeks. We got into straight Go code, so there was no AST walking. The compiler is very gracious, you know, it optimizes, you get very optimized code. I don't think you can get any better unless you go into the assembly or into the, you know, interpreted like language that is being compiled by Go. The only small, very not small issue that specifically static language like Go has is that it kind of compiled it into an SO plugin, and then you got to do plugin open. and load it. And when you start to dig into the plugin framework that Go has, it's very, very limited. So what do I mean by limited? When you compile your code, you got to compile it exactly with the same packages and versions that you used initially in your collector. So you compile a collector, and then you got to know exactly what version you use when you compile it. That's the first. And second, when you load a plugin into Go, it kind of loads into memory, and that's it. You can't unload it. You're stuck. So if you want to load and dynamically change OTTL, you're going to have a bad day eventually. Like, you're going to keep loading plugins until you run out of memory. You're going to lose data to a customer. So, you know, we kind of got stuck. So we've done that. We solved the problem. I'm going to show you some numbers pretty soon, but it wasn't good enough for real production. So it worked for one customer. That's nice, but it's not scalable. And that was, we fought the end of the journey. I didn't release it into open source because I didn't feel comfortable with that solution. It seemed to be too limiting. And let me know if you actually want that release. That's fine, I can do it. But for about 6 months, we got stuck. We said, okay, we're not sure if we're going to get any other customers that have this kind of problems. But, you know, we did. We were running into additional customers, and we need to do this one-off solution for them, compiling, loading a plugin, getting, you know, excellent results in terms of performance. But we got stuck. What do we have here? We have a little bit about how the evaluation looked like, how we parse the condition, and yeah, I think a lot of things I already talked about, so I'm gonna go over. So a function that being generated, you kind of skip everything on the left. So over the left side, you see how we walk over the AST, and we go into a Boolean expression. We need to walk over every leaf and every part of the syntax tree. In comparison, in code, you basically go and get an attribute. You know, you do some validation and comparison, but it's very, very straightforward. You know, it generated code. It doesn't look good, but it's very optimized. And it turned from this thing into, you know, 57 nanosecond with 2 allocation into like 8 nanosecond and 0 allocation. And that just for a simple expression. When you go into more nested trees, it becomes quite a nightmare in terms of allocation and speed. So we're talking about 7x just for this simple expression. So I talked about the trade-off before, but let's go over them again. So we got like between 3 to 12x speedups, near 0 allocation. There's still small allocation that we didn't work on optimizing, but I quite honestly believe that you can get into zero allocations. So it's really nice. But again, you got another thing that you got to be dependent on SCaLE, which is not that nice. If you want to be without any, you know, you're in Docker, you don't really want to be, you want to be headless. You don't want to have any dependencies. So with plugins, you have to use SCaLE. So you got to have some C library around, and you got to have some Linux there. And you got to compile. That was another issue, by the way. Compilation takes a lot of time. You know, so what we wanted to do initially was to load the collector, has some code there in the Docker container, has like an initialization step where it compiles the OTTL expression and then load it into the collector. But that took a few minutes. So, and also you're very limited, you know, running in a container in Kubernetes in a customer's side. So it's like what they're gonna pay every time they load a container. That like doesn't make sense. So you have to build an infrastructure where you compile it somewhere else, and you need to know exactly what collector version they have, and then you need to deliver it. So it's a nightmare again. So seems like a very good solution, but not really. So what did we do? We came up with a very nice idea, very neat idea called Closure Combinator. So what do we do now? So we can walk the AST And by the way, I'm not going to take credit for this idea. This is all thanks to coding agents, I think Codex. I don't remember which one that I used. I don't remember when, around October maybe. So before the new models are even better. So maybe there's better ways to do it. Who knows? Just, you know, prompt away. So before that, we walked an AST node, resolved the path. We need to box values, turn them into interfaces, which means a location, and do some type assertion, compare, and return true, false, based on the comparison that we're doing. If we're talking about filtering, it can also do transformation, of course. And now what we do is we basically parse expressions. And the idea with closure is you take every leaf and every part and turn it into a function that you can compose. So you can think about it like functional programming. Like you have a lot of small utility functions, and at load time you compose them together. And then instead of traversing a tree, you basically already have a function that calls a function that calls a function, etc., 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 until you actually get the result. And you know, surprising enough, it turned out to be almost as good as the compiled version, and in some cases even better, which honestly surprised me. I didn't expect it to work so well and to be so elegant. So again, we moved from 5 steps into a single step, but without any heavy lifting, right? The only thing we needed is basically to build a lot of small utility functions, which nowadays, when coding is not as hard as it used to be, is not such a pain in the ass. It's like we were able to do it. So a deeper dive into how it actually looks like. So you have your code on the like an example on the left, which is turned into. So you gotta get a key, right? So you're building a getter, and then you're building a small function that can do comparison, but for string, and you need to have the same function for every type that you have. And of course, you're also going to have a generic one that does boxing for the case where you need to compare objects that you're not familiar with. But you can always optimize it. You know, if you see that you're dealing with a type that you never met before, you can support it as well. So, and eventually you compose everything together. So in this case, you take is_error and compare it with, do an AND over 400, and the over 400 is make int 64 greater than. So it compares, you know, get code and with 400, and you know, you can go over all the small functional composition that we have, the nice composition, and you get into the same you know, like relation to an AST, like the same representation. That's what I looked for. So all the composition of the AST is done at the generation time. I guess it's not really compiled, but very similar. And at runtime, it's just functions. So there's no AST. You don't need to assert types. You don't need to do any allocation. So boxing, again, you gotta do, you gotta deal with that. The way we've dealt with boxing is we turn that generic any translation into many small functions that allow you to basically get, extract the value based on the type. And you have all of that when you generate the code, so that wasn't that big of a problem. And then your composition becomes very type specific. So this is an example of comparison for string. So when we're doing the compilation or the generation, we're basically trying out with the thing that we know are usually the one that are gonna occur. So string in the case of the telemetry data that we usually see is the type that we usually that come first. So we try to do a comparison for that, and then we move to the next one. And that's only for the generation, right? In the actual runtime, it always know what the type's gonna be. And then, okay. and then the also path resolution. So attributes and can also be nested because you can have map that points to with a key that points to a value that's a map, and so on and so forth. So all of that can also happen using some code that can go through that, because again, in OTTL expression, you kind of represent where you want to go, so you can build the retrieval function using composition. So here's the before and here's the after. We got from about 255 nanosecond for our location, just an example over the things that we ran. And for our location into 0 location, and when you look at the actual heat map, you see that you basically get into the actual retrieval. So the thing that you gotta do, because you eventually end up, you process telemetry data, you gotta go and retrieve and do comparison and do those checks. You gotta do that in Go. So we reduce about 27% of CPU overhead. There's no more AST traversal. There's no allocation. When we're talking about more complicated expression and all the composition, we got into about 40x improvements without any garbage collection pressure. When you talk about the breakdown of the expression that we have, simple, you can think about simple as just a simple comparison without any end in between. The more complex is a lot of expression that has logical operation between them. Very complex, also contain regexes and groks and things like that. And then, of course, you have nested path that basically means you got to retrieve, you got to check the type and things like that. So that's even more complicated. And here, the interesting thing is the closure one was actually, I ran this benchmark and updated it yesterday. And it really surprised me that the closure was more performant than Codegen. I didn't dive into why, so I can't tell you. The only the only thing that remained for us is basically regexes. So what about regex? So when you're talking about the Go regex is not that efficient. It's really nice, but Intel released something called Hyperscan a while ago that uses the specific SIMD acceleration instructions, and it's really fast. And then on ARM, you have vector scan. I didn't try it yet, but I really believe that if we really want to take the collector over the edge, when it comes to performance, we should invest in supporting these two different, form of algorithms or libraries, and potentially we can get like 50x. So if your operation is very dependent on regexes, that's something to consider. I don't really have a good solution for Grok yet. Grok is also a nightmare when it comes to performance. So I guess my next presentation is going to be about Grok or something. So what we eventually end up shipping is a closure combinator. We're in the process of also releasing it in open source. I didn't start the conversation in the Open Telemetry Committee, the collector meeting that they have every week about any of this. So there's still road to go, but on our personal, like Sawmill's contribution, contrib of the Open Telemetry Collector is going to be released in the next few weeks. So if you want, you can use it. And again, the best trade-off between the compiled one is the speedup, but in my opinion, it's not just that, it's the, you don't really need any compilation, you don't really need to know exactly what is the library, so all the surrounding, all the mess you need to manage is gone. You basically have very speedy load up initialization that's not very different than the evaluation of OTTL. What we learned, always start with measuring the HA proxy. We should have thought about that in the beginning, but eventually we added that. We now ship it in every any distributional collector, I really recommend putting something before the collector so you get some better visibility in terms of compute and memory. It's like almost zero. It's really worth the hassle of having another sidecar and configuring an HA proxy. So that's you know, a good tip. I was surprised by the allocation and boxing and AST. I actually assumed that, you know, the OTTL and AST is like the best we can get to, but I was surprised that it's not, and that's actually not that efficient. Compilation is always the best, but when it comes to Go, which is a very static language, when it comes to, you know, they don't really like loading things, loading code. It didn't really turn up, and you know, safety is always better than speed in most cases, even here. Yeah, any questions? Yeah, yeah. So we saw that the latency wasn't good, but what I mentioned was the P80, P90 percentile. So most of the time we thought everything was fine, and we assumed wrongly that the latency came from sending data, you know, outbound. We wrongly assumed that there's high latency because of the exporter, not because of the valuation, because it like doesn't make sense. Usually in something like the collector, you would assume that I/O is going to be the problem and not you know, CPU. Like it doesn't make sense, right? Like you think about the collector, it's like, okay, what's going to be the bottleneck here? It must be I/O. So we're like, okay, so there's latency because those guys, you know, downstream don't know what they're doing, something like that, and that was the wrong assumption on our end. Yeah, exactly. When you use something like HA proxy, you basically say, I'm going to use an external process that is not dependent on any CPU or memory to really understand what's going on. And in our case, we were very curious about the I/O, you know, networking. So it gave us visibility and also allow us to, I think the best thing for our customer was the fallback mechanism. So while we were figuring this out, we could actually tell them, look, yeah, we have an issue that we're not really processing and reducing your cost, but at least we're not losing any data. So not great, but, you know, better than where we started. So we figured out that it's the CPU, and we started doing the P profiling. Like we started profiling it on our machines. So we yeah. So what we've done to figure out whether you're asking how we figured out that CPU was the issue, right? So what we've done was we basically took a lot of the telemetry data from with the permission of our customer, and then we built a sort of a benchmark testing library, and we checked what was the issue. We actually sent data downstream, and so and like P profiling you see it in a second. If you do some P profiling, some profiling to the processor, you basically very fast you see those flame graphs that show you exactly where the issue is. So we done that, and immediately we saw that the culprit was actually the OTTL evaluation and not the I/O of sending something somewhere. Another interesting bit is we didn't really see high CPU. Like when we looked at the collector, we didn't really see high CPU. And you know what? To this day, I don't really understand why there's no. Like it got stuck, but the CPU was never an indicator that it got stuck on evaluation. I don't know why. Yeah, exactly. You could, and it's very, very hard to get to zero fallback, like to zero. In our case, like getting into zero fallback became our target, and it's very hard because even if you're set, like we can have an entire talk about how to do auto scaling to the collector, which is also very hard. Like, how do you do auto scaling? Do you use a sending queue, for example? Yeah, like sending queue is another big lesson in general, I'm saying, that we had when it comes to production, like taking the collector into production grade. Because you want to have the ability of like have some queue that would allow you to batch data, not batch, but like store data before you send it somewhere in case there's some issue, right? So that's another very important thing. But yeah, you basically wouldn't know if you're losing data. You might be losing data now and you don't know it. Yeah. Any other questions? Yeah. Every time you do what? Yeah, so you're asking, let's see if I understand the question. Every time we change filters, we need to do this closure combinator again? Yeah, basically, yeah. Every time, and it's the same thing with OTTL in general. Like when you define some OTTL expression, right, and you put it in a transform processor or filter processor or anything else, and you load the collector, usually people don't really load it dynamically. They turn off the collector and turn it back on. What happens is there's an initialization phase where you take, it only happened once when the processor loads, where you take OTTL, turn it into an AST, and then the AST is there, and when traffic starts coming, you basically walk the AST over every log message. So a new log message arrived, and then you like the collector, traverse the tree. What we're doing is something very similar. We're taking the OTTL, and instead of translating it into an AST, we do another step. So we still do the same AST thing because like it's very helpful, and then we take the AST and we translate it into a function that we compose on top of another, and that's like closure combinator. That's the name of this pattern. We didn't invent it. So yeah, you got to do it every time for OTTL when the OTTL changes. Yeah. Oh, like. Yeah, but you know what? Like it's you're when you're doing plugging and you're loading code, the trick that the plugging authors did is you load it in memory. You load it in memory into the process as if it's part of the original binary. So there's no. Yeah, exactly. Yeah, so that's why it's like native code, and that's awesome. But it also have a lot of limitation, and nobody really thinking through right now about what's gonna. You know, I don't know. But I'm not aware of any active work to make it better. Yeah, yeah. That's why I'm here talking about it. Yeah, because I agree. I didn't see anything like that in Go. Yeah, you're welcome. Any other questions? Yeah. All right, guys. Thank you so much for coming. Yeah, I'm Amir. If you